Welcome. In this video, we're going to be discussing the IPR for horizontal well producing undersaturated oil and with pressure drop along the wellbore. So consider the following configuration. We have the lower part of a horizontal well in which we have an open hole part, and then we have inserted a slotted liner which has packers, and then that liner is hanging on the lower part of the casing. So in the previous derivations we have done, we have assumed that actually all the pressure in all the part of the well that is exposed to the formation is simply constant. So we're going to plot that. I'm going to plot it from, it's a bit strategic for later, but from left to right. Okay, we're going to say this is X. This is from 0, which is the toe, to the heel, which might be located at L, all the part that is exposed. And I'm plotting the pressure. Okay, so that pressure is simply constant. And here I'm referring to the pressure which is inside the wellbore. Is P that I will call PW. P inside the wellbore. PW is constant. And we're saying, well, simply this PW is the flowing bottom hole pressure because it's constant. And then we found an expression earlier that PO, rate of oil at standard conditions, is pressure, reservoir pressure minus flowing bottom hole pressure. But in reality, that's not the case. Typically, what we have is that we have a variation of pressure. Sometimes it might be very small, sometimes it might be relatively big. That we have a variation of PW along the wellbore. Okay, and in that case, we want to see how will that affect our IPR, or if I can still use this linear IPR that I derived earlier. Okay, in this case, remember also we don't have, we need to define where the bottom hole pressure is. Something that people typically do is, well, they say RPWF, bottom hole pressure, is the point which is easier to measure, is closer to surface, is the last point where I have inflow from the formation, and that might be that point, okay, the point at the heel. Okay, so how will that affect? Well, we know that if we say, we know that the derivative of pressure, how is the pressure changing along the distance? Okay, the pressure along the wellbore. This is actually given by density of oil. If I'm assuming it's only oil flowing here, friction factor, then we have the diameter, and then we have velocity squared divided by 2. Okay, we're assuming that there is no change in elevation. It's a perfectly horizontal wellbore, and also is liquid and is relatively incompressible because the change in this term in kinetic energy is not much from toe to heel. Okay, so I'm neglecting that part also. So I'm considering only the friction part. Okay, we know that velocity I can express in terms of the local rate of oil. This will be at a given position, so it's a wellbore as a given position W. We know if we plot that along the wellbore, this is X. We have here L and 0. So if we plot that, initially this QO is going to be 0, but then it's going to maybe increase. Okay, this is the Q oil in the wellbore. Okay, and without the hat because it's local. Okay, it's at local conditions. And that divided by the area. Okay, but I can also say that Q oil, we usually, the IPRs, we don't work with the local volumetric rate. We work with standard conditions rate. So this could be the standard conditions rate at any position in the wellbore. This is a function of X. Okay? And this is this times the BO, again, and any position W is going to be equal to that QO. Okay, that's simply the relationship or the definition of the formation, oil formation volume, volume factor. Okay, so I substitute that into that equation. I end up with the following: dP and the area, of course, the area is the cross-section area, so I'm saying this is pi over 4. Okay, it ends up being like that. Okay, when I substitute this, all of these definitions, I substitute it here, and I end up with this equation. Maybe here I'm missing a square. Okay, so as you see, actually what I have in this equation is that it becomes is nonlinear. Essentially, I have a quadratic term and I have this friction factor, which is also highly nonlinear and is nonlinear. So when I here in the formation, I might say, well, the flow is linear, but then when I put it together with something that is nonlinear, well, actually, I should end up having something that is nonlinear to an extent. Okay, how much this affects the linear part, we are not sure, and that's something we're going to investigate further. But essentially, what we see is that if we're going to plot the IPR, we should find is that instead of having something like this linear, well, we might have something that is nonlinear. Okay, maybe something that is like that. Okay, when we consider the pressure drop along the wellbore, well, we see this is an energy loss, so we really shouldn't have more than the case where I assume that I don't have any energy loss along the wellbore. Okay, so we kind of intuitively we think that this should be below. Okay, another thing to look into this equation, maybe we can use that equation to do our calculation. What we see here, we have a variable, which is the pressure along the wellbore. This we don't know. Okay, all of these are properties and equations that we can find out. Okay, and here we have something else that we don't know. How is the Q of oil changing along the distance? Okay, so we have like an ordinary differential equation, which is nonlinear, and we have two unknowns. Okay, so we need one more equation to solve to at least one equation with the same unknowns. Okay, so we're going to follow the steps of Ben Dicken, who was publishing this paper in 1989. Okay, he was an engineer with Shell, and he came up with this process, slightly different. He solved it in a different way and having slightly different assumptions, but essentially it's very similar. Okay, so the other equation we're going to use is we're going to use mass conservation in the wellbore. Okay, that means that if I have, let's say, on my wellbore, remember I have this slotted liner, and I have here is QO, standard conditions at the wellbore. And actually, at every position X, I also have flow from the formation that I'm going to call I. Okay, the I stands for influx. Okay, so at every position, because it's a distributed influx, I'm going to have an influx of I. So if I make max conservation in the wellbore, I end up with the following equation, that the variation in the mass of the oil that is being transported in the wellbore is actually simply equal to how much is going to come from the formation. Okay, so that kind of makes sense intuitively, that if you say that this number is coming in, then this one is going to increase. Okay, if I have influx from the formation, then this one is going to increase. It's going to get bigger and bigger with distance, just like what we express here. Okay, now this influx, how do I express that influx? I have to find a way to connect it to this pressure at the wellbore. So another assumption we're going to make is that we are going to say that the influx is made out of, so we know we already found the equation for the complete near wellbore formation. Okay, we know that this has, if the pressure is constant, we know that this behaves in the following way. Okay, for all the total flow rate and assuming that the pressure is constant. So what we're going to do is we're going to say we're going to split this in infinitesimal, very small slices. Okay, each one will have its own pressure. And we're going to say that we can express the rate coming from each one of these slices, which is exactly the I influx that we need, with a J times PR minus the P of that particular wellbore, of that particular position. Okay, and that J is going to be the specific productivity index, and it's going to be J divided by L. And this has units of standard cubic meter per day per bar divided by meters. Okay, so we have like the rest of the puzzle that we needed. So we have now this equation, which is dQO dx equal to small j times PR minus PW. Okay, and we have also this other equation that we derived, that is this one here. Okay, so these two equations make up, if you see, I have two unknowns here, QOW and PW. But here I have also the same two unknowns, PW and QOW. In this one I'm deriving QO, and this one I'm deriving the pressure, but essentially it's both. They are ordinary differential equation. This one is linear and this one is non-linear. Okay, and I basically have to solve these two simultaneously. Okay, to solve it, remember, to solve any ordinary differential equation, we need to have initial conditions. Okay, and for that we need to know at a given x, at an x, okay, star that we don't know, we need to have the values of these two unknown variables. Okay, and I'm going to choose strategically because I know that at the toe actually have no flow. That value should be 0. Okay, so I'm going to say, well, strategically at x equals 0, then this is going to be 0, and that pressure, well, I don't know what value that will pressure have, but I will say simply it's an assumed value. Okay, I'm going to assume a number, and then it should be, of course, less than reservoir pressure, and then I solve it and then see how it gives. Okay, so that's essentially what I'm going to do. So I'm going to solve that using Python. Okay, and for that, I'm going to share with you, it will be in the links of the video, it will share with you this, I've decided to run Python using a Jupyter Notebook, and I have decided to run the Jupyter Notebook in the environment called Google Collaboratory. That is available if you have a Google account, so then you have access to, it's like a small computer on a web server in which I can run Python code. Okay, so first, see here, I'm loading some libraries. This library, matplotlib, is to plot. This library, scipy, is to do the solving of the differential equations. And this numpy is to make simply operations. Okay, so I'm going to run that square, that block. Okay, it's connecting, it's assigning me a machine in Google. And then I just run that. Yeah, and here it shouldn't give anything interesting because simply it's loading the libraries. Okay, now the second block that I have is the definition of the functions that I'm going to use. So I need the friction factor, and to calculate the friction factor, I need the Reynolds number. Okay, so I have programmed this. And then I have this equation, which is actually this equation dpw dx, which is actually this equation that I have here. Okay, is this equation to the left. That's what I have here. Okay, and one thing which is important is that this expression, the density and the BOW, and the BO, these are fluid properties, so this depends on pressure. Typically, there is isothermal, so it should also depend on temperature, but as the temperature is constant, so I'm assuming that the pressure is the variable, is the value that changes these properties to change. Okay, so if you see here what I'm doing, I'm first changing the units because typically I'm using the oil in standard conditions, and then I'm finding BO and I'm interpolating on a file. If you see the file here, I have a file. I don't have it here. Maybe I should upload it. Okay, here I have that file. If you see that file, what it has? It has what we have used before, so pressure and temperature. The temperature is constant 100, the pressure is changing from 400 to 5, and you have BO, viscosity, and density. Remember, you need densities in the equation, and to calculate the friction factor, you need the Reynolds number, and the Reynolds number, you need also the viscosity. Okay, so this is actually interpolating using this NumPy library is interpolating with pressure on that matrix, and then this one indicates which column to use. Okay, if it's going to be 0, so that will be pressure is in the 0 column, then temperature is number 1, then BO is in number 2. Okay, so that's where you have these two here. And then viscosity is in number 3, so here viscosity is reading it from number 3, and density is in number 4. Okay, we could have used simply a constant values, but I think it's important, as we have mentioned, that these properties, they change and vary with pressure. We should take their variation in pressure considered into account. Okay, for that returns actually this equation, friction factor, density, velocity, and I calculate the velocity using all the same equations that we mentioned before. Okay, then you have the other equation, which is this one. How is QO changing along the wellbore at standard conditions? And this is simply the specific J times reservoir pressure times PW. Okay, and then I have to, this is simply the way how I solve it in Python. You have to program this function that actually splits these two terms, these two derivatives. Okay, simply is using u, which is a vector that is using to progress the solution. So this is the vector at initial time. Okay, so it's taking the element number 1 or element number 0. Index 0 is PW. Okay, and the other is this one. So actually here the equations are the opposite. Okay, this is the first one, and then this is the second one. Okay, so that is going to be used later to solve this system of coupled nonlinear ordinary differential equations. Okay, so I have said here using data from a previous example, length of the well, 1,000 meters. I have used a diameter of the wellbore of 0.1, a J, total J of 64, roughness of the pipe of the liner of 1 to the minus 5, and reservoir pressure of 300. Okay, properties here I'm loading the file pvt That's why I need to have it in this folder. So let's first run this block, which is a function. And then now I'm calculating the specific J, which is the big J divided by the length of the well. Initial conditions, I'm saying here you see Q of the tow is 0, of the oil at standard condition that the tow is 0. So that's the same one that we have here. This is 0. And then PW, we say we know reservoir pressure is 300, so we have to assume a value lower than that. Okay, so we assume 200. And then that's my vector of initial values. And then I have to discretize, say for how many points in X I want to solve this solution. I said, well, use 100 points in this 1,000. And then this is where I'm actually solving the system of equations. And this ODE is, ODEInt is a function that is part of this library called SciPy integrate. Okay, so what is happening here is that I'm solving, I'm getting the results, and I have to follow the same order. So the first one is going to say wellbore pressure, and the second one is going to be a standard condition oil rate in the wellbore. It's going to be these two. Okay, simply that you can find out an example how to do it on the internet, but simply that's how you solve this system of equations. Okay, it shouldn't be, it's not the main point of this lecture. Okay, so now it's solved, and now I'm plotting, and what I'm going to plot is I want to plot along the distance, so along this X that I said, I want to plot how is the Q oil inside the wellbore. Okay, I call it here QW, but in reality it should be this QO, W. Okay, and it was already run, so it's a bit cheating, but it tells you initially 0. Okay, and then at the heel is going to be the full rate of the well, which is something below 7,000 standard cubic meter per day. Again, you see actually that is relatively linear, and that means that actually, well, the inflow might be very uniform, because if you have that shape, that means that, well, what is coming in every section of the wellbore is actually uniform. Okay, so here I'm looking at on that vector that I have this Q max. What is the maximum? Is a bit below 7,000, as we mentioned before. And now I'm going to plot, this is the rate, and now I'm going to plot the pressure at the wellbore. Okay, and the pressure you see from 200 that I had at the toe and it's going down to maybe 170 or something like that. Okay, and you see that it's actually non-linear, the distribution of pressure along the wellbore. Even though the distribution of rate is linear, this one is non-linear. Okay, and the pressure at the heel, or what I call the flowing bottom hole pressure, is 176. So that's very fine. I solved it for 1 point. Okay, but really what I want to know now is the IPR. Okay, I want to know essentially this famous equation that we have been looking at here. Okay, that we say is the relationship between PWF and QO. So one way to do that is I can repeat all of this process. Okay, if you see here the PWF is 178, 176. Okay, so I will have 1 point in my IPR. Okay, if I now, because I made this run in my Python script, okay, and then I find that PWF and my QO, this is 6,870 something, 780. Okay, standard cubic meter per day, and then that should go with 178 bar. Okay, this is in bar. Okay, so that's my first point. Okay, and you have, of course, the one which is the reservoir pressure. Here you have 200, and then you have 0. Okay, at 0 rate. No, 300, sorry, was the reservoir pressure. So if you want to produce more points, one way to do it is simply to change this initial condition. I can simply assume, well, now the pressure is not 200, but it's something different. Okay, so that's what we are going to do. We are going to repeat this process for different values of assume of PW, and then we are going to plot this series of points. So the way that's done, again, not, we don't want to go much into detail into that, but I say, well, I want to put 100 values. My IPR should be made up of not 110 values. Okay, I'm going to make a vector that goes from PR to this minimum to 200 to 100. Okay, 10 values, and I'm going to create these vectors that are going to collect the results. What is PWF and what is the Q oil total? Okay, so for that, for each one of them, I'm first, this is the initial conditions. The rate at the toe is always going to be 0, but then the pressure at the toe is going to change depending on the number that it has on that vector. Here I'm solving the system of ordinary differential equations. Here I'm reading the results. And here I'm appending actually the maximum value of oil rate in the wellbore. That will be what is being produced. And then I'm appending also the minimum value of the wellbore pressure, which is the flowing bottom hole pressure. Okay, so I'm running that process many times. Okay, well, 10 times to find these 10 points. And then finally, I'm going to make a plot here, and I'm going to plot the initial IPR, which was neglecting the pressure drop at the wellbore. Remember, this one was using 64, a J of 64. Okay, and I'm going to plot this solution, the results that I obtained. Okay, so here this is plotting the results that I obtained. IPR considering delta P in the wellbore is going to be in black. Okay, and then this is going to plot these values here. You see that I'm taking yeah, I'm here. I'm building the IPR considering no delta P in the wellbore, and then I'm plotting it. This is using simply 64, and you see that's what I obtained. Okay, so you can see that actually our suspicions were correct. That we have a linear IPR if we consider no delta P in the wellbore, but if we consider the delta P in the wellbore, it starts becoming non-linear. Okay, so now let's do some sensitivity tests. So for example, we can say, what if we have a bigger wellbore? Now the wellbore won't be 0.1, but 0.2, for example, and we run. Okay, you see now the pressure drop is almost nothing. Okay, you see that the pressure drop for 200 is almost nothing. And then if we see the IPR, you see actually that it falls very much onto the linear IPR with neglecting without considering the pressure drop in the wellbore. But now if I use a smaller wellbore, okay, now let's say that I have 0.07, for example. Okay, now you see it starts to be the influx starts to be nonlinear. That means that I'm getting seems to be getting more flow from the part of the wellbore that is closer to the heel than closer to the toe. Here is uniform. You see the pressure drop for 200 is actually quite dramatic. It's on 200 at almost 20 something towards the toe. And let's see the IPR. And here you see how the IPR looks like. That actually have a significant, is affected significantly by the delta P in the wellbore.